Swayam Prabha. Digital India. Educated India.
Before I go into something very interesting one, which is very, very interesting in terms of the electron counting of a molecule, metal carbonyl, but they are not. So, if you consider a metal carbonyls, okay, metal carbonyl, so far I talked about all monometallic, FeCO5, vanadium CO6, mostly I talked about manganese CO5 minus. So, these are all monometallic. So, the metal carbonyl can also be a multimetallic. Name one compound which is a bimetallic, like a cobalt 2, manganese 2, right? So, if I ask you about a trimetallic, trimetallic is your Fe3CO12. Trimetallic system, Fe3CO12, ruthenium 3CO12. So, these are trimetallic. So, I can go on and on and on, and I go all the way up to 12 metal, M12. And we do not know how many carbon monoxide gas will be there, okay? Sorry, carbon monoxide ligands will be there. So, this is something different. Like more you go, like if you have a monometallic system, what is the typical electron counting rule? 18 electron. If you have FeCO5, you can simply say 18 electron rule and this molecule is stable, this is this. Bimetallic system, Fe2CO9. If you take FeCO5, if you put it in the sunlight, you get Fe2CO9. You all read about it, no? It converts into Fe2CO9. Then you have a trimetallic, tetrametallic, so on and so forth. So, up to trimetallic, you still can follow the 18 electron rule and get the electron counting, even also 4. So, you have another molecule, cobalt 4 CO12, you heard about it? Cobalt 4 CO12. So, I am going little bit further away from the monometallic to the multimetallic system. So, if you have a multimetallic system, what will be the electron counting rules that would tell you exactly what is the formula? So, if I put 11, so you may say, sir, this is not 11. I do not know what is the number, but this is not 11. But who will tell you that? Someone has to tell you, right? If I say, oh, this molecule is not aromatic, sir, this is anti-aromatic. Who told you that? So, there is some formula, there is some rule. So, in this case also there is some rule, okay? I will come back to that. But up to here, you still can work with 18 electron, okay? Let us say with the same number 12. How you do that? First of all, you need to calculate the electron first. So, first calculate the electron. You have how many metals? And first thing I have asked you in the beginning, what would be the geometry? Tetrahedral, square, planar, or butterfly, right? Now, let us see how many electron first. Cobalt, how many electron? 9, 36. CO 2 into 12, 24. Total how many? 60. How many metals you have? How many metals? 4. So if you need to follow 18 electron rule, so 4 18s are 72. So this, if you consider 18 electron rule, all the metals should have 18 electron. So that means it should have 72 electron. How many got? 16. So there's some problem. But how you can make it 72? So you see the difference. 72, 60, 12. So 12 electron shortage. How you can make this 12 electron in your molecule? Adding, very good. So 18. So I know I had given you the formula. I cannot go beyond that. Okay, this is the formula that you have, and you have to tell me what is the geometry and so on and so forth. So there is a shortage of 12 electron. This 12 shortage electron, you can make it by 6 metal-metal bond. So that means this molecule has 6 metal-metal bond, and what will happen? So 6 metal-metal bond, each bond gives 2 electron. So that means now you calculate. This will give you this 60 electron with 6 metal-metal bond, and you get total of 72. So that means this follows 18 electron rule, in which all the metal will be having 18 electron all, right? But the moment you cross more than 4 metal, like 5, 6, 7, 8, so on and so forth, then you cannot follow the 18 electron rule, and for that one general rule has been developed by Mingos, DMP Mingos. Okay, this is all there in your textbook. I am going to give you a general formula for that rule. There are so many things I wanted to, but time is very short. Okay, so the rules are, so first one is your 18N, and this is meant for your that organometallic compound in which you have a metal. Then if you have, so this is a monometallic, then you have 16N plus 2 linear, then you have 16N ring compound in which N greater than equal to 3, N greater than equal to 2. Now if you apply these rules and see where this can take you there. Okay, so this is a 18 electron, N equal to number of metal. So then you get N equal to number of metal means you have a 1 metal, then you get a 18 electron. Now if you have, n equal to number of metal or number of vertices. Vertex means like you have a tetrahedron, you have a 4 vertex. You have a trigonal bipyramid, you have a 5 vertex, so on and so forth. So in this case, if you have this formula, then it's a linear. If you have a 16n, then you have a ring compound in which n equal to number of vertices. So now, utilizing this, you can predict what would be the structure or the geometries of those molecules. Now, before I go into give you further details on the rules in which you can predict what would be the shape of this molecule, you need to understand few things about the geometry. Suppose if you have a one metal, it's a simple metal, you have simple, use the ligand, you get the octahedral geometry, put metal in the center. Now, if you have, let's say, geometry n equal to 4, that you have already told me, square planar or tetrahedral. N equal to 5, square pyramid or trigonal bipyramid. N equal to 6, octahedral. Any other? That is octahedral. Square bipyramid and octahedral, what is the difference? Any other geometry other than octahedral? Pentagonal? Pentagonal pyramid, great. So first is you have your octahedral, then you have pentagonal pyramid, any other geometry? N equal to 6. Very common geometry, you can, anyone? Trigonal prism. You never saw this geometry, trigonal prism. But this is a very common geometry. Trigonal prism. You have 3 square faces. So you have a octahedral, you have a pentagonal pyramid, you have a trigonal prism. This is with n equal to 6. Should I go far? Let's see how good you are. N equal to 7? Very good. Next. Pentagonal bipyramid. Okay, I will not go beyond that. N equal to 8. So these are all very common when you talk about a transition metal complexes. ML6, what is the geometry? Octahedral. Like all those octahedral complexes, crystal field theory of how the ligand gives and your energy gets splitted depending on the strength of the ligand. If you have like very strong ligand like CO, CN, you're splitting energies and all those things, you read it in the octahedral, tetrahedral. So now, this is organometallic chemistry, we are not talking about transition metal complexes. We are talking about a geometry in general in which we are dealing with a number of vertices. If you have a number of vertices 7, pentagonal bipyramid. What about n equal to 8, 9, 10? Let's see how n, 8, 9, 10. Huh? 8. You are very smart. Every time you are putting cap. Okay, fair enough. Hexagonal bipyramid. Correct answer. Any other geometry? There are two more geometries which are very important one, which are all there in your talking about Wade's rule and how the shape of a molecule would determine and all. And they are your square antiprism. Heard about it? Huh? Square antiprism and how you so you have one square here and you also have one square here. So this is called square antiprism, okay, in which you have n equal to 8. Okay, square antiprism and your bicapped hexagonal pyramid. Now the good thing about this square antiprism geometry is that if you know this 8, now you can put a monocap square antiprism and you can make a bicap square antiprism. So that gives 9 and 10. Okay, you understood? Little difficult, as I told you earlier, I will move from a very easier one to, and I have not gone through the 10, 11, 12, which probably you need to know of those geometries. These are very important one. So the square antiprism geometry is very important because you can generate 9 and 10. If you remove one capping, monocap, square antiprism. If you remove both the capping, you get a square antiprism. If you cap them again, monocap with 9, n equal to 10, you have bicap. Capping with a square is very easy because it's like a square pyramid. You're just putting a cap on your square face. This is a square face, you are putting a cap. It's a square face, you are putting a cap. So 9 and 10, you can generate it from the square capping of the square antiprism. So that gives you 9 and 10. Another very important geometry of 9, there are many molecules there in the textbook, like the one example is rhenium H9, 2 minus. Rhenium H9, 2 minus. How many ligands are here? What type of ligands are they? X type. So what is the oxidation state of rhenium? This is 2 minus. 7. 7 plus, right? Now what is the geometry of this? How many ligands are there? 9 ligand. What is the geometry? A wrong answer. I'm sorry, but not necessary that you know one geometry, you put the, okay, this is a geometry. Not, like not all the student in IIT, they look alike. Like rhenium H9 is a particular student and that will be completely different from what you are here. So all the molecules, not necessary that if you have a 9 ligand and it will be a monocap square antiprism which you just learned. Okay, so the geometry is tricap trigonal prism. Trigonal prism geometry I had shown you earlier. This is a tricap trigonal prism in which you have how many square? 3 square, and what I have told you, tricapped. So that means you have to cap This is monocapped, bicapped, tricapped. So this is tricapped trigonal prism in which all the vertices has hydrogens. And rhenium is in the middle, coordinated with all the 9 hydrogens. Okay, now if I ask you, can you draw tricapped trigonal prism? If I ask you, draw it here? No, not now, maybe give me some time. Okay, but this is one of the very, very important geometry. I'll do it again for you. Okay, what you need, this geometry also you did not know, that is trigonal prism. Very important geometry, extremely important geometry. Trigonal prism, what you have here is three square faces. 3 square faces, 2, and you have one here, 3. So what you get here is 1 here, 2, 3. So 3 square faces. What you need to do, Sandhya, now? Cap them. Cap what? Square face. So you know how to cap the square pyramid. So let's say this is a square and you need to, so you have a monocap trigonal prism. Now if I ask you what is the geometry of a 7 vertices, you can tell this also. Monocap trigonal prism. If I ask you another cap, this is bicap trigonal prism, you can say n equal to 8. If I tell you the tricap trigonal prism, n equal to 9. It's very simple. If you know one answer, you can expand this to a different one, right? Okay, so you know about the geometries of the metal carbonyl in which you have a lot of metals, a multi-metallic system. Okay, you need to determine the geometry of that, but I think that would be, like that is called Mingo's rule. Okay, that I had given you 3 formulas. One is 18N, in which N equal to 1, so that is 18 electron. If you have N equal to 2, that is called 16N plus 2, that will be a linear. Okay, then if you have a 16N, N equal to greater than equal to 3, and that gives a ring compound. Like if you take, can you do for me Fe3CO12? Fe3CO12. Fe3CO12 and predict whether it's a linear or ring compound, depending on the formula I had given to you. I had given a formula 18N, 16N plus 2 and 16N. I had given you a formula, you need to predict whether this is a linear or ring. Done? I had given you a formula Fe3CO12. First thing you need to calculate the number. Fe how many? 8. 3 8s are 24. 12 2s are 24. So 48. So 48, what is N? What is N? 3. Now put the formula 16N or 16N plus 2. Which is matching? 16N. And what is 16N? So this molecule actually is a ring compound. Okay. So based on the formula, you can predict whether it's a linear or ring. It's not that, like 3 metal, Fe3, if I give you another example, like manganese 3 CO some number, it also has 3 metal, but it's a linear. That gives 16N plus 2. So depending on the number of electrons, the molecule will show the geometry. This is given by a particular formula. I had given you so far 3. You want to get more, you can predict further. Okay, I'll give you 2 more. One is your another one is called 15N. 15N, you have a 3 connected clusters. You let me know when you are tired so that I'll stop it. You are not tired yet? Sure, not hungry? Very good. 15N. When you have a 3 connected clusters, what are those 3 connected clusters? You all know it. You have the given examples to you so far. 3 connected clusters. You have the clusters you have seen so far. I had given you tetrahedral. Draw the structure of tetrahedral quickly. If you draw the structure of tetrahedral, what you see here, anyway, pay attention to me. All these vertices are 3 connected. 3, 3, 3, 3. This is called tetrahedral. Now tell me other clusters in which all are 3 connected. Another examples I had given to you just now. Trigonal biprism. Sorry, trigonal prism. 3, 3, 3, 3, 3, 3. Any other examples? Very well known, all of you know. That is what? Cube. Check it. 3, 3, 3, 3, 3, 3, 3. So if you have this kind of clusters, you can use blindly 15N. So that means what will be the procedure? You will get a formula from me. Okay, let's say I will give you a formula. Okay, let me just do this one quickly, you will know this one. Rhodium 6 C CO15, a carbon 2 minus. Okay, so if you look at the formula, rhodium is equal to 9, 9 6 is 54, you have 15 carbon 30, you have 2 electron and you have 1 carbon 4. What is the total? 4 plus 90. What is N, Sandhya? Rhodium 6. 6. Which formula fits here? 15N. 3 connected. 3 connected, 16 vertex. Which geometry will fit? Only one. That's trigonal prism. So that means if I give you a formula and if I ask you to predict the geometry, you have no other choice but trigonal prism. So this is the power of this electron counting rule. There are many more will coming. So that means whatever things I had told, Fe3CO12 we have seen it's a ring compound. Then if I give you, let's say cobalt 4 CO12, please do it quickly. Cobalt 4 CO12. Cobalt 4 CO12. What is the number? Cobalt 4 60. What is N? What is the formula now? 15N. N equal to 4. Tetrahedron. This is also 3 connected. What is the written? 15N 3 connected. You have also, there are many more examples in which it is 15N and you can predict the structure, like there are many examples with a cube. Cube means N equal to 8 and you can give the formula fits into that. So this is 15N. Okay. So now I had given you 4 formulas on electron counting. One is 16N plus 2, 16N, 18N and then 15N. Now whatever things you have learned so far, next one is your called 14N plus 2, 14N plus 4, 14N plus 6, so on and so forth. This is called closo, this is called nido, it's called arachno. Okay. Now what is N? N equal to the number of vertices. N equal to number of vertex. Right? I will give you some formula. Okay, after 18N, 16N plus 2, 16N, 15N, it goes to 14N plus 2, that is closo, then nido, arachno. Okay, now I will give you a formula. You have to predict what is the shape or the structure. Osmium 5 C CO15. Can you tell me what is the structure or the shape? Osmium 5 C CO15. Give me the number. Okay, first one, osmium is 8, is Fe, ruthenium, osmium. Osmium is 8 electron. So 8 5s are 40, 40 plus 30. Osmium 5 C CO15. Huh? 74. Which formula will fit here? What is N? N equal to 5. Which formula fits? Nido. It is nido. So square pyramid. Square pyramid means nido. So if you start with something, let's say this is octahedral. So this is octahedral means closure. So you remove this one minus n vertex. You get a square pyramid, that is Nido. If you remove another one, then you get a arachno, that is butterfly. Okay, anyway, now can you do me the second example, rhodium 10, which is 9 electron, 90 phosphorus is equal to 5, and you have a CO 22, 44 plus 3 minus, what is the number? Rhodium equal to 9, so 90 plus 5 plus 44 plus 3. Who said closer? Very good, you get a brownie point. But tell me, what is the geometry? Closo n equal to what? 10. Just now I shown to you. 10 vertex closo, bicap, square, antiprism. Bicap, not tricap. Bicap, square, antiprism. So you are getting there. I'll give you a last example. You know, if you remove one more vertex, you get this 14n plus 6, that is arachno. Now 14n plus 2, n equal to 12. What is the geometry? And what is the electron count? 12. Number, I'll give you the example. Okay, if you take this example, rhodium 12, tin, CO 27, 4 minus. So I'll do it for you. Rhodium 12 means 9. 9 12 is a 108. Tin equal to what? Tin is in the group 4 family. 4. Then 27 into 2, 54 plus 4 electron. What is the total? 1. And which formula it fits? 4n plus n equal to? So 14n plus 2, n equal to 12, this gives 170. So n equal to 12, n equal to 12, closure geometry, what is the structure? So this is one of the most important structure, probably you heard it or not heard it, I do not know, called icosahedral. Icosahedral geometry, in which you have it's a little difficult. I am doing it for last 30 years. So I can understand, probably if you practice you can do that. But this is one of the most symmetrical geometry. If you anybody interested in boron chemistry, this is B12. B12 icosahedral geometry, and in this case this geometry also fits into this because this is 14n plus 2. So there is another geometry which I have not told you, that is called octadecahedron, 11 vertex. Okay, that you can check it in your textbook. All right, so I will stop it here because I know we are getting little bit. Okay, so with this, let's stop it. I wish I could have continued. I don't know how many of you are interested in to learn more, but nonetheless, I'm traveling to IIT Bombay at 4 o'clock flight, so I won't be able to take further class. But I wish that I could have taken one, but I'll definitely share the textbook to Professor Anberson, probably by which you can read them more. And these are extremely important in terms of when it comes to organometallic molecule, the geometry is very small thing. If you can build it up and go and see how nicely, it's like a math, or it's like like aromatic molecule, organic molecule who were like 14n plus 2, like what do you call that, aromaticity? Thank you. And anti-aromatic, aromatic system, or aniline system, and you can predict whether it will follow or not. So this chemistry, particularly metal carbonyl, organometallic, or in particular boranes, they are very nicely fits into all different kind of electron counting rule. Another electron counting rule, like we should be very proud of this fact that one of our professor from IIC Bangalore named E.D. Jamis, he is a Padma Shri, and because of developing another electron counting rules where the other electron counting rule failed. So this is very important. It's called MNO rule, which is a little bit difficult at this stage. I can see that if you go further, it will not be, and they are not in the textbook here. But nonetheless, I wish you all the best. Do well. Be in touch in case you need to, and I'll share some details so that you can read it for your second year of MSc, whatever be your curriculum. Okay, thank you all.
Swayam Prabha, Digital India, Educated India.